If you walk into pretty much any plant manager office and ask how their air system is doing, 9 times out of 10, they will just throw a CFM number at you. Like, oh yeah, we make 1200 CFM, we are good.
Right, like cubic feet per minute is the only metric that matters.
Exactly. But CFM is just volume. It doesn't tell you if your tools are starving, if your air is full of moisture, or if your machine is about to overheat and blow itself up. That is why on this episode of the Big Dog Podcast, we have got to talk about the real performance pyramid.
Okay, so what actually makes up that pyramid then? Beyond just raw volume?
It comes down to 3 things: pressure stability, duty cycle, and downstream air quality. If any one of those 3 is off, your plant productivity takes a hit.
Wait, let's break down pressure stability first. What does a good pressure band even look like at the point of use?
In a properly configured network, you ought to be holding your pressure within a tight plus or minus 1.5 psig band. When you swing wildly below that, air tools bog down, automated cylinders misfire, and you end up turning the whole system pressure up higher just to compensate, which wastes a ton of energy.
So you are paying for extra power just to mask a control problem.
Every single day, yeah. And then you hit duty cycle, which is where people get really caught off guard, especially with light-duty reciprocating piston compressors.
Recips, right? I mean, small shops run recips all the time. What is the issue with running them hard?
They are structurally limited to a 50% duty cycle. That means for every 30 minutes it runs, it needs 30 minutes of sit-down, shut-off cooling time. If you push a light-duty recip past that 30-minute mark in an hour, the pistons run blazing hot.
And compare that to a rotary screw compressor, right?
Right. Industrial rotary screw air compressors are engineered for 100% continuous duty. They are built to run flat out, non-stop, without overheating.
Okay, but what happens when somebody tries to mix those two technologies on the same line? Like putting an old piston unit in as a backup next to a newer screw unit?
Oh man, that is where you run straight into the $200 check valve disaster.
Wait, the $200 check valve disaster? What is that?
So every time a recip piston strokes, it shoots a pulse of air into the header. Pulse, lull, pulse, lull. A receiver tank dampens it, but it does not get rid of it. If you tee a recip into the same header as a rotary screw and you forget a simple check valve,
The pulse travels backward?
it hammers backward right into the rotary screw air end. The pressure spikes slam into the bearings. I have personally seen multi-$1,000 air ends completely destroyed, bearings chewed to pieces, all because nobody put in a $200 backflow check valve.
Wow, a couple $100 in hardware versus thousands in destroyed bearings. That is a brutal oversight.
It really is. And those recips run so hot too. I was on a shop floor a while back, and the operators were literally cracking open the manual ball valve on the bottom of the receiver tank, leaving it hissed open all day just to bleed off water.
Wait, they left a valve open continuously just to drain moisture?
Continuous air leak, on purpose. Because the recip did not have an integrated aftercooler. That extreme cylinder heat degrades the oil super fast, increases oil carryover, and sends wet, dirty air downstream to ruin the tools.
So, you are leaking compressed air that you paid to generate just to fix a heat and moisture problem caused by the wrong compressor choice.
You nailed it.
Okay, so if reciprocating units have those duty cycle limits and pulsation issues, rotary screws seem like the logical default for most manufacturing plants.
They are the absolute workhorse of modern industry, no question. Especially when you get into 2-stage rotary screw designs.
How does the two-stage setup improve the efficiency numbers?
By splitting compression into 2 distinct steps with cooling in between, a 2-stage rotary screw delivers about 15 to 20% more flow per kilowatt hour compared to a single-stage unit of the same size. The energy savings alone usually pay off the higher initial purchase price in about 2 to 3 years.
That is a pretty quick payback. But there is a trade-off, right? What about downstream air quality?
Yeah, with oil-flooded rotary screws, you will get a tiny bit of oil carryover. We are talking a few parts per million. For metal fabrication or general assembly, nobody cares. But if you are in semiconductor, pharmaceuticals, or food and beverage, even a fraction of a ppm of oil can ruin an entire batch.
Which is why those sensitive plants often look at oil-free options or large centrifugals. But centrifugals have their own hidden trap, don't they?
They really do. Centrifugal compressors are dynamic machines. They don't trap air in chambers, they blow it with high-speed impellers. So for massive, steady baseload demand, say above 400 horsepower, they are smooth, efficient, and completely oil-free.
Zero pulsation, oil-free air, huge flow. That sounds ideal on paper.
It is ideal until your plant demand dips. Centrifugals have a very narrow turndown range, usually only about 25 to 35%, managed by inlet guide vanes. If plant air demand drops below that range, the compressor approaches what is called the surge line.
What happens at the surge line?
If flow gets too low, the pressure in the plant header overcomes the output of the impeller, and air tries to flow backward through the compressor. To prevent that violent surging, the controller opens a blow-off valve and vents air straight out to the atmosphere,
Wait, so it is just dumping compressed air outside?
dumping it straight to the birds. And here is the kicker. The compressor is still drawing around 70% of its full power while dumping that air. You are paying for all that electricity, and almost half of what you produce is just blowing into the parking lot.
That is an energy nightmare if your demand fluctuates wildly during a shift.
It will wipe out all your efficiency gains in a heartbeat. That is why there is no single winning compressor type for every factory. If you need massive steady baseload, centrifugal wins. If you need high continuous duty with variable demand, a rotary screw with variable speed drive wins. If you have tiny intermittent high pressure demands, a recip wins.
So performance isn't about buying the biggest or most expensive machine on the market. It is about balancing pressure stability, duty cycle, and air quality against how your facility actually operates day to day.
Exactly. Understand your load profile first, align it with the right compressor design, and protect your system with proper controls and check valves.
That wraps up our quick take for today. Thanks for tuning into the Big Dog Podcast. We will see you next time.
Take care, everyone.